Jennifer Martinez here, and welcome to tangent line approximation, also known as local linearization. Here is the formula. It says, suppose f is differentiable at a. Then for values of x near a, the tangent line approximation of f is given by f of a plus f prime of a times x minus a. The expression on the right side here is also called the local linearization of f near x equals a. We are thinking of a as fixed so that f of a and f prime of a are constant. So by the way, this is just the tangent line at x equals a. So let's first see how the formula comes about. To find an equation of a tangent line at x equals a, we're going to use the formula, our tangent line formula, where x1, y1 is the point A, f of a. And the slope is going to be the derivative at a. If you just plug that in, y1 is f of a, m is f prime of a, x minus a, and you add f of a to both sides, you get f of a plus f prime of a times x minus a, which is the right-hand side. So what we just found is the equation of the tangent line. I'm going to call that y tangent, and it's this red line right here. You can see that when you were close to a, that red line is a good approximation to the actual function. So that's why they have, so f of x is approximately equal to that tangent line approximation, or that tangent line near x equals a. So therefore, f of x is approximately equal to our tangent line. And you get that formula. Here's the actual f. Now, when you go to how far they went, you can see that there is an error, and it gets farther and farther away from the true value, depending on the concavity. The error function, call it e of x, is defined as this distance right here. It is for each point that actual f of x value minus that tangent line approximation. So that's all that is here. So let's go ahead and try an example. What is the tangent line approximation for f of x equaling sine of x near x equals 0? Example 1 in the book. So that's our function on the left. To find the right side, I'm going to find f of a. In our case, a is 0. So sine of 0 we know is 0 degrees, or is, well, it's in radians, but still 0. So we have the point 0, 0. And we know the slope is the derivative at the point, and the derivative of x, I guess I should write that somewhere, f prime of x, we know is cosine of x. So f prime of a, in our case f prime of 0, is cosine of 0, which is 1. So now if I go ahead and figure out what that is, that tangent line, it's going to be f of x is going to be approximately equal to f of a, which is the 0. Let's just write it down here first. F of a plus f prime of a times x minus a, which is the 0 plus 1 times x minus 0. So you actually get x, don't you? So f of x, which is sine of x, that's our actual value, is approximately equal to x near x equals 0. And this x is also called the local linearization. You could have also found it just by finding the equation of the tangent line. So let's go ahead and look at a picture of this. So here's our actual function. And then again in red, let me do the equation of the tangent line or linear approximation. You can see that as long as we're close to 0, that is pretty close to the actual function. If you want to test it, let's check values close to 0. So here is the answer, and I'm going to check values like maybe 0.1, maybe 0.5. 0.1 turns out to be 0.0998, which rounded to 1 decimal place is 0.1. 0.5 is 0.4794, which again is pretty close to just the x value. Let's try one more. Let's try 1. Let's go all the way to 1. What would sine of 1 be? Sine of 1, not so close. Maybe I can do 1 down here. That is 8415.8. That gets a little off. Let's try 0.75. 0.75 is also a little off. 0.7, a little closer. So you can see the farther I get away from 0, you could do negative values too, the less approximate it's going to be. If we wanted to find the error, we could subtract the real value minus the actual value. So here the error of each of them. So if I look at 0.1, I'm going to subtract the real minus the approximate, the real minus the approximate. Here are the errors. You can see that they get bigger and bigger. They are negative because it's the real minus the approximate. You can see the approximate is an overestimate because it is concave down when x is bigger than 0. But if we chose negative values over here, it actually would be an underestimate, and then these would be positive. So this is a good way, if you, especially if you did not have a calculator, and you wanted to find approximate values, an easy way to find the approximate values of sine of x near, this one is x equals 0, but you could do near x equals whatever value you're looking for. So let's do another one. Let's find the local linearization for square root of x near x equals 4. So this is going to allow us to approximate the square root of 5 or the square root of 4.1 or 4.5. So let's go ahead and do that. So again, I'm going to let f of x equals square root of x, and then I'll take the derivative. We know it's 1/2 x, the negative 1/2, or 1 over 2 square root of x. We're near x equals 4, so f of 4 is 2, and f prime of 4 we know is 1 over 2 square root of 4, which happens to be 1 over 2 times 2, which is 1/4. So we have a point. So this would be, the point would be, this one is 4, the x is 4, y is 2, and we have the slope. So you could just use your tangent line approximation if you want, or you can use our new formula. So this would be a 2, 1/4, x minus 4, or if we use our handy dandy formula, we would get the f of a, which is the 2, plus f prime of a, which is the 1/4, x minus a is the 4. And this would be approximately square root of x. So if you add the 2, you would get that. So either way you would want to do it. But you notice if you leave it just like this and not actually multiply that about, you can actually then look here, check out square root of x and our approximation. So we'll call this 2 plus 1/4 times x minus 4. If we compare those three, so let's do things near 4. So what did we say? We were going to do 4.1. So square root of 4.1, we could figure that out on our calculator. And this one would be 2 plus 4.1 would be 1/4 of 0.1, which is approximately 2.025. And if you plug in square root of 4.1 in your calculator, you can see how close that you're going to get. What about 4.5? What about, well, here are the actual values. If you do this, you can almost do this in your head. This would be a 4.5 minus 4, which is 0.5, which is approximately, or which is equal to, I should say, 2.125. You can see how close that is. This is actually equal as well, I realize. Right? It is approximate to the value, but these two are equal. And then 1, well, that would be 5 minus 1, which is just 1. So that would be equal to 2.25. So these are the approximate values for square roots of things near 4. So the answer for the local linearization would just be just this. If you want to multiply that out, you're more than welcome to as well. You can write it like that, or you could write it as 2 plus 1/4 x minus 1, so it would be 1 plus 1/4 x. Would also be a great answer.